Okay, this one is lesson 103, your second spring break assignment. Again, kind of a straightforward lesson, shouldn't be too difficult. Okay, first off, this one again we're talking about logarithms. Logarithms are used when we have really large numbers or really small numbers. And in the old days, we would do a lot of estimations with logarithms because the numbers were so large to deal with. Now it's just you're pretty much using logarithms when your calculator cannot do it. For example, which is larger, 872 raised to 148 or 781 raised to the 162? If you put those in your calculator, the calculator is going to give you overflow, which means it's more than times 10 to the 99th. So what we do instead is we change these very large numbers. We say, well, this now is the exponent that 10 must be raised to give us 872 raised to 148, and this is the exponent that 10 must be raised to. And from then we can figure out which one has the largest exponent, and then that gives us the largest number. Alright, but that's what logarithms are used for now, more than estimations. Alright, remember a quick review of our rule of logarithms. A logarithm is an exponent. In this case, I've got common log, so it's the exponent that 10 must be raised to give me a. Well, if I'm adding exponents, right, x cubed times x squared is x to the 3 plus 2. So if I'm adding the exponents, what am I doing? I'm multiplying. So this is the log of a times b. And a number times an exponent, let me put it over here, x to the 5th cubed, that would be 3 times that exponent, x to the 15th. X to the 15th. So a number times an exponent is log of n raised to the m. The coefficient comes up and becomes an exponent, or sometimes we do it the other way. The exponent goes out front and becomes a coefficient. If I'm subtracting exponents, what am I doing? I'm dividing the arguments, right? R divided by Q. Alright, so we're going to use this idea. Turn this one off, turn this one on, we're right on that one. We're going to use this idea to write this one as a single logarithm. The title of this, I believe, is Calculations with Logarithms. It's actually logarithm expansion and logarithm contractions. So this one's going to be a logarithm contraction. We're going to write this as a single logarithm. Alright, so first thing we're going to do is we're going to take all these coefficients, this coefficient, this coefficient, and this coefficient, and we're going to bring them up and make them exponents. So this is going to be the natural log of x squared minus 1 cubed minus the natural log of y squared, whoops, I missed one, minus the natural log of x plus 1 raised to the 4th plus the natural log of y squared plus y raised to the 2/3. Okay, now I recognize that some of these are being added. This one and this one are being added, and these two are being subtracted. So if I'm adding, they're multiplied, so this just becomes the natural log of x squared minus 1 cubed times y squared plus y to the 2/3 divided by, these are being subtracted, so now they're in the denominator, they're divided by y squared times x plus 1 to the 4th. Alright, so that one, I don't know if we're going to simplify this. X squared, yeah. So writing this one, did I copy the problem wrong? X squared minus 1 cubed. Oh, now the fun part becomes simplifying this algebraically. Let's see if we can do this. So this is going to be x plus 1 cubed times x minus 1 cubed, right? Because this x squared minus 1 factors into x plus 1 times x minus 1. Excuse me. And here I'll get y to the 2/3 times y plus 1. Factor that one out. Y plus 1 to the 2/3. Well, y factors out. Me with y to the 2/3, y plus 1 to the 2/3. This is just x squared and x plus 1 to the 4th. Now what happens here, this one cancels all but one of those. Let's see here, y to the 2/3, and this would be y to the 6/3. So I think downstairs I'm going to get y to the 4/3. So this becomes the natural log. So downstairs is y 2 minus 2/3, so that would be 6/3 minus 2/3 would be 4/3. Y to the 4/3, x plus 1. Let's see, what do we have upstairs? We have x minus 1 cubed, and then y plus 1 to the 2/3. So it's actually, the algebraic simplification is more work on this problem than the actual contracting this down into as a single logarithm. All right, let's look at another example. Okay, this one is going the other direction. This one we're going to expand into the sum of logarithmic expressions whose arguments are linear. That just means raised to the first power. Raised to the first power. Okay, this one has x and y cubed multiplied, and then all of this downstairs is being divided. So let's rewrite this first. Rewrite this as the log of x y cubed divided by, now I'm going to rewrite this as x plus 1 to the 1/2 and z to the 3/2. X plus 1 to the 1/2, z to the 3/2. So now this is going to be the log of x, and now since this is multiplied, it's going to be plus the log of y cubed. Now what's downstairs, what's being divided, we're going to subtract the log of x plus 1 to the 1/2 minus the log of z to the 3/2. But what we see here is that it asks for us to linear. Arguments are linear. So the first one's linear, so that argument, log of x. But how do we make y cubed linear? We take this 3 and move it out front. So it becomes 3 times the log of y, and then the 1/2 comes out front, put that in parentheses, minus 1/2 the log of x plus 1, and then minus 3/2 the log of z. Alright, so that's that. Alright, so that's what I mean when I say logarithmic expansion was the previous problem. This is a logarithmic this one's logarithmic expansion. The previous one was logarithmic contraction. Alright, another purpose for logarithms, again, when the numbers get real big or real small, it's easier to use an exponent. The example that we tend to practice with is pH. We know that 10 raised to the negative pH is equal to the concentration of the H plus ions. Rewriting that exponential equation as an logarithmic equation would be compounds, substances pH is equal to the negative log the concentration of the H plus ions. So very quickly, if you're asked for what is the pH of a solution where the H plus ions is 4.03 times 10 to the negative 6, you just put this straight in your calculator. The pH is the negative log of 4.03 times 10 to the negative 6. So that negative 6 could come out front, but we're just going to put that straight in our calculator, and we'll get a pH of 5.4. So the pH of this solution is 5.4. Alright, again, in the old days we would have to do a lot of estimating on that, but with the calculator not so much. Now going the other direction, if you have a pH of 7.05, what is the concentration of the H+? Well, the concentration of the H+ ions is equal to 10 raised to the negative pH. So it's going to be 10 raised to the negative 7.05, where the concentration of the H+ ions is 8.9 times 10 to the negative 8th. 8.9 times 10 to the negative 8th. And the units of this, what are they? Moles per liter, I believe. Yeah, it's molarity, moles per liter. 8.9 times 10 to the negative 8 moles per liter. All right, enjoy the rest of your